All right, linear equations aside for a minute, we're going to try and generalize things a little bit more here. And when we work with linear equations, right, we just talked about how we can generate their graphs maybe by, putting in x's, getting out y's from a table and using that table to help generate values. And generally, when we're working with equations, right, any point that is plotted on a graph would correspond to a solution, right? And that solution would have an ordered pair associated to it, an x and a y, right? And that's what we have here. When we think of a collection of ordered pairs, we typically call that a relation. There's going to be somehow we have x's that relate to y's. We don't necessarily always have a rule, but there's just a collection. So we have that as our relation. Specifically, when we're in the relation, all the x values, all those inputs, make up the domain, and all the y values make up the range, right? We've probably heard these words already. Okay, one specific thing that we are going to see over and over and over is this concept of a function. And so a function is a specific type of relation. Okay, so you can have relations that are not functions. A function is where every domain element is assigned to exactly one range element, okay? Or similarly, every x has one y, okay? Sometimes thinking about the opposite understanding helps us identify when it's not a function. So if, and I want to highlight this, if a relation has the same domain values assigned to two different range values, then it is not a function. So if we have like 2, 2 and 2, 3, not a function. Okay, so for instance, when we look at this graph below, you might know other ways to determine, if it is a relation or not, but what we can do is, okay, so first it says, list the ordered pairs of the relation. Okay, we can do that. And so I did that. I would enclose that collection of ordered pairs in curly braces. Okay, and so that's what I would have for my relation. And then the domain, right, the domain would just be all the x's from there. So I would say it's, okay, -3, -1, 1, and 4. If I have repeated elements, I don't need to list them multiple times. And the range would be all the y coordinates, all those second coordinates of 5, 0, -6, -2, 2, and -4. They don't need to be in order. Okay, a set is just a collection, doesn't matter how you arrange them. And then determine whether or not it's a function. So now I need to think, okay, x's, right? Does every x have just one y? And I'm going to say, no, it is not a function. So if I look at like these 3 points, right, I have repeated x's and they're assigned to different y values. So that's not a function, okay? Not a function. Okay, we want to be on the lookout for this concept of a function in every relation because we get some extra utility, some extra tools out of a function. Okay, for instance, when we see y as a function of x, right, we get extra notation. And what that means, mathematically, we could write it as like y is equal to f of x. So if you see f of x notation, that's the same as y. But it also means that there's a rule that takes x, if you give this rule f, right? You do some operations on f and you get out y. Okay, so it's a machine. So sometimes you might have, or previously you may have seen, okay, we put x into the conveyor belt in this f machine and the machine spits out y. Okay, same idea. Okay, the other thing is that, yes, we have x as the input, y as the output, but then also for every x, we get exactly one y. Okay. And then lastly, when we have this sort of understanding that y is equal to f of x, y is a function of x, we do need to recognize that the variable y is completely isolated in the equation. Okay, so for example, if we're trying to determine, whether these things are functions of each other or not, we specifically y is a function of x, right? That's y equals f of x. Y needs to be isolated, so if I isolate y, 2 plus x squared, right? There is, here, I have to ask myself, if I give one x value, do I get out one y value? I'm going to say, yes, it is a function. That's my, FCN is my abbreviation for function, okay? By comparison, right, if I solve for y here, I'd have y squared is equal to 1 minus x, and then to solve for y, I'd have y is equal to square root 1 minus x, and when I introduce the square root, I need the plus and minus, okay? Because of the plus and minus, right, I have 1x, I pick negative 2. Negative 3 would actually be a better example. I pick negative 3 for x, run it through, I get out, plus and minus 2 for y. Because I get two y values for one x value, this means that it's not a function. Okay. Last one, I want you to take a shot, solve for y, and then ask yourself, if you put in 1x, do you get out 1y? There you go, there's the answer. And then so if you do have it as a function, you could write f of x notation instead of y. So f of x equals 2x squared, and then this other one would be f of x is equal to negative 3 minus 4x. All right. And then lastly, one of the other things we need to do with functions is be able to use the notation fluidly, right? And so when we have a function given to us, we want to be able to evaluate. So when we see g of 3, we have to recognize that, oh, this is replacing x in the equation, right? And so to evaluate this, I would just take the equation, and wherever I see an x, I would replace it with that value. So minus positive 3 squared, positive 3, and then evaluate. So follow PEMDAS. Let's see, this would be 27 minus 6 plus 1. Let's see, so that's 28 minus 6 is 22. Okay. And so then next one, I'll let you do on your own. I'll fill in the solution here in a minute. G of h squared. This is where, okay, we're like, oh no, it's not a number. It's totally fine. It's just same principle, right? 3, and then wherever x was, replace it with what we had, and then, or what we're given, and then minus 2, and then replace that, and then plus 1. Okay, so put h squared in those locations, and I just get 3. Following rules of exponents, 3h to the fourth minus 2h squared plus 1. Easy peasy. Okay, and then the last couple here, I want you to pause the video, try it, and then resume when you're ready to see the solutions. And here are the solutions. Okay, so the first one is kind of one that I think might be a little bit easier, right? We just do g of x, so take that whole function, and then write that down, and separately calculate g of 2, which ended up being 9, and so then combine the two using like terms. The second one is the one where we probably end up wanting to do something similar to what we did in the first one, but it ends up being a little bit more complicated, right? We have to replace the x in the 3x squared minus 2x plus 1 with something that is two terms, the x plus 2, okay? And the x plus 2 requires us to write out 2 copies of it, boil it out, collect like terms, all that. So I did that fast over on the right side in green, okay? And the other thing too is that we need to remember that this minus ends up distributing, right? So you get minus 2, minus 2x minus 4. Okay, so I encourage you, if you didn't get my answer on that one, go back through slowly and try it again, all right? So point of all this is function notation, there's a lot embedded into it. Certainly we have one input, one output as the overall idea behind it, but then also using it for evaluation purposes is super critical too.